Hello everyone, welcome to our YouTube channel Electronics Maddie. Today we're going to talk about KVL, KCL, voltage division rule and current division rule. So let's get started. Kirchhoff's current law. It's actually named after a scientist called as Kirchhoff. It is one of the most fundamental laws in the history of electrical engineering, just like Ohm's law. So Kirchhoff had a thought process of how to solve electrical networks. If you take any device in real life, for example, a TV or a computer, it basically consists of a lot of components. And if you want to simplify the equivalent representation of a circuit, you need to apply KCL and KVL. And in order to determine the amount of voltages and currents across each and every branch, you need to understand the idea behind KCL and KVL. So, what is Kirchhoff's current law all about? So, the statement of Kirchhoff's current law is the algebraic sum of currents meeting a junction or node in an electrical circuit is zero. So, in order to understand this statement better, let's have a pictorial representation. So, let us consider this as a circuit. With respect to this, you see O is the node or a junction. A junction is a point where two or three electrical components meet at a particular point. So, for example, in this case, we have five currents I1, I2, I3, I4, I5, and out of which I1, I2, I3, and I5 are entering currents, and I4 is leaving current. So, what is the statement? Referencing with respect to the figure over here. So in order to understand that, let's have a common convention of how the sign of currents are supposed to be taken. So when current is entering a particular junction, we will be taking it as positive. When current is leaving a particular junction, we will be taking it as negative. So once we have this common in thought process, we'll be able to try and simplify and understand what statement of KCL is all about. So you can also have a reverse convention as well, but this is just to have a clear indication. We'll be following this convention throughout our videos. So let's get started. So plus I1. So I1 is the current entering. So we will be representing it as positive, and it's represented as we are representing it as plus I1. So now I2 is also current entering. So we'll add that plus I2. I3 is also current entering. So we'll take it as plus I3. So I4 is current leaving. So we'll be taking it as negative. So it will be minus I4, and I5 is again current entering. So we'll be taking it as I5. So it is equal to 0 according to the statement. So what it says, the algebraic sum of currents meeting a junction or node in an electrical circuit is 0. So the algebraic sum of all these currents is equal to 0. So what is the next step? If we try and solve this using a mathematical analysis, you will be getting I1 plus I2 plus I3 plus I5 is equal to I4. I4 is transferred to this RHS side. You will be getting this equation. So what does this give you an indication of all about? Can the statement be further simplified to have a clear understanding of what KCL is all about? So sum of currents entering the junction is equal to sum of currents leaving the junction. So yesterday I spoke about one of an example where when a tap is open, the amount of water that is there in a bucket will be the amount of water that is supplied from the tap. Just like that, if you have considering another example where a group of people are standing in a queue, person entering the queue will be equal to the person leaving the queue. So it's as simple as it is. So that means whatever current we are supplying, that will be the current coming out. So we can say that summation of current entering is equal to current leaving. This is the simplest statement of KCL. So you have to remember only this point very clearly whenever you're understanding the concept of KCL. These are extreme basics with respect to electrical engineering. So once you are aware of what KCL is all about, we can get into our next concept, that is KVL. Okay, so what is KVL? What is the statement of KVL? Let's see the statement and then try to correlate with an example as how it can be done. So the algebraic sum of all voltages in any closed circuit is zero. So let's consider a few of the conventions initially. It basically shows three representations with respect to resistor, a battery, and a battery with respect to a source. So what is our general convention is that if you're having a resistor and current is flowing through it, we will consider the first end as positive and the second end as negative. And if it is a battery, we will be considering it as the first end as positive and second end as negative. Similarly, we'll with respect to the source as well, we'll be considering it in the same way, irrespective of the direction in which the current is flowing. This is our normal convention. You can also analyze this in opposite way, where you can consider it as minus plus, but this is our general way of consideration. And while writing equations, whenever it is from plus to minus and whenever it is living, so if I is living, it's entering at positive and it is living at negative, that means we have to write it as minus VR. Similarly, if the current is entering plus E and then it is living at minus, so we'll be writing it as minus E. So I'll be showing that in equation that will be clear for you. So just to give you an understanding, let us consider a circuit. This is a normal circuit with a DC supply and resistive branches that are there. Two DC supplies are used in this case. So let's consider and apply KVL across A, B, C, F, A. So A, B, C, F, A. So this is the loop where we will be applying KVL. So be very careful with respect to understanding this. It's clearly mentioning the algebraic sum of all the voltages in any closed circuit. That means the circuit should be closed before applying KVL. You cannot apply KVL for an open circuit. This is the common mistake that everyone does with respect to the thought process that are involved in higher studies especially. So be very careful with this basics. So let's now apply KVL. At this point, let us say current is now we are considering the direction from A, B, C, F, A, right? So from A to B, you see the voltage source E1, so minus to plus. So it's ending with plus, so we'll be writing it as plus E1. So from B to C, next we have is we'll be writing here it as plus and we'll be writing here as minus. So we will be considering voltage drop across R1 as V1. So we can write it as minus V1 because it's minus over here. So next from C to F, we can again write it as plus with respect to resistor and minus with respect to R2. So we'll be writing minus V2 as I mentioned with respect to this convention that we are following. So again from F to A we don't have any other branches, so we'll be equating it to 0. That is what the statement says. So the algebraic sum of all the voltages in any closed circuit is 0. So once this is done, we can simplify this further as by transferring V1 and V2 into the RHS side, and we can write E1 is equal to V1 plus V2. This is one of the equations. Now let us consider another loop from this point, that is E, D, C, F, E. So we'll again apply the same process. Like let us the current flows in this direction. We are assuming the conventional current to flow in this direction. So now from minus to plus, it's moving. So you will be saying it as plus E2. Again, now it's if we write this as plus, and if we take at this point, it's plus, and if it's minus at this point, so we will be writing it as minus V3. Again, when you come down through to this particular loop where you see the branch CF resistor R2, we'll be taking plus here and minus here, so we'll be writing it as minus V2 again. So again, there's no branch elements here, we'll be writing it as 0, and we'll be equating it to 0 because of the statement. So once this is done, we can write E2 is approximately equal to V3 plus V2. So what does this say? Whatever is the supply voltage, say E1 in this case, and the voltage drop across these 2 points, this is V1 and this is V2. So whatever is being supplied, that only will be available as voltage drop. So there is a fundamental law where energy cannot neither be created nor be destroyed, but it can be transferred from one form to another. Same thing applies here. Whatever you will be supplying, that is what you'll be getting across these resistors. So that is what I'm trying to say. So E1 is a supply voltage. So voltage drop across R1 is V1, voltage drop across R2 is V2. So whatever is supplied will be equal to the sum of drops across these 2 points. Similarly, E2, with respect to E2, E2 is a supplied voltage, and the drop across R3 is V3 and drop across R2 is V2. Again, the sum of the voltages E2 will be equal to V3 plus V2. So whatever is supplied, that will be the drop across these 2 points. So it's a very clear indication of what KVL is all about, and what can be concluded with respect to KVL is our important observation that needs to be made. So sum of voltage drop across each component is equal to the algebraic sum of EMF in that loop. So that is what I'm trying to say. Sum of voltage drop. So these are the sum of voltage drop across this particular loop. So that is always equal to the algebraic sum of EMF in that loop. We have EMF with respect to this loop, it's only E1 with respect to this loop. So summation of E1, like if you have another EMF that is connected in series with this, we'll be adding both of them and summation will be equal to V1 plus V2. So as a conclusion, we can say sum of EMFs is equal to sum of voltage drops for that particular loop. We can also call that as IR drops. So because according to Ohm's law, V is equal to IR, we usually voltage drops V can be written as IR drops as well. So that is with respect to KVL. So once you have a clear understanding of what KVL is all about, let's get into our next concept, that is voltage division rule. So first thing to remember is it's with respect to series combination. So this is the fundamental thing that you have to remember. So what is series combination? What is parallel combination of resistances? It's told in our previous video. So please to watch it if you want to get a clear picture of it. So what is voltage division rule all about? So let us suppose there is a network like this and you want to find the voltage across individual resistors, say R1 and R2. As I clearly mentioned, with respect to series combinations, there will be voltage drop across resistances. So you have to remember those 2 points in our previous video. So if V is the supplied voltage, so what will be the drop across R1? I want to find the voltage drop across R1. I want to find the voltage drop across R2. So in that case, how do you do it? There is a simple analysis that will be carried out, and we'll be coming at a common conclusion, and that will be applicable universally to all the circuits that are there. So let's get started with it. So we know for a series combination, the effective resistance is the sum of the individual resistance values. In this case, we have only two resistors connected in series. So some of you might have a confusion that how are they connected in series, because they look parallel to me. It's not that case, because they're connected end to end. The resistance R2 end is connected to R3, and it is again connected to the supply. Just because the image is rotated, it doesn't mean they are connected in parallel. So be very careful with this analysis as well. So RS is equal to R1 plus R2 according to our series combination effective resistance. So now from Ohm's law we know that V is equal to IR. So what can be done? We can write I is equal to V by R, isn't it? So the next step is I'll be writing I is equal to V by R1 plus R2. The effective resistance RS is what is represented here. R can be written as R1 plus R2. So I'm writing it over here and labeling it as equation 1. So once this is done, we can write voltage drop across R1 by applying Ohm's law. V1 is equal to I into R1, isn't it? So similarly, we can write it for V2, but before that, we can simplify this expression. So V1 is equal to V into R1 by R1 plus R2. How are we getting this? We are substituting for the value of I from equation 1 in this particular equation. From here to here, when we are substituting I in this equation, we will be getting V into R1 by R1 plus R2. So we have one equation here. Similarly, can we write voltage drop across R2 as V2 is equal to I into R2? So again, we can substitute for the value of I. So V2 is equal to V into R2 by R1 plus R2. So commonly looking at these two expressions, what can we say? We can write it in general as Vx is equal to V into Rx by Rs. So if you want to find V1, substitute x is equal to 1. So V1 is equal to V into R1 by R1 plus R2. This is the effective resistance. Again, if you want to find V2, we can write it as substitute for x is equal to 2, V2 is equal to V into R2 by R1 plus R2. So if you want to find the voltage across that particular branch in general, so if you want to find the voltage across R1, so V into the resistance value divided by the summation of the total resistances. This is voltage division rule. It is as simple as it looks like. So the major purpose of inventing this particular rule is to find the individual drops across each of the components that are there. So once we are clearly aware of it, we can go to the next concept, that is current division rule. So it's applicable for parallel combination because the current divides in parallel combination. Again, if you want to understand how resistances in parallel combinations are connected and basics of it, you can refer to our previous video. So with respect to this, you can clearly see current is dividing as I1 and I2. The currents I1 and I2 might not be same, it might be different. So first step, we'll start off with our analysis in this way. So the effective value of resistances in a parallel combination can be written as 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3, which is explained in our previous video. So this can be further simplified as Rp is equal to R1 R2 by R1 plus R2 if there are only two resistors that are connected. So in this case, we have only considered two resistors, isn't it? So we'll be writing Rp is equal to R1 R2 by R1 plus R2. So what is our next step? We'll be finding the currents I1 and I2. That is our objective here. So please understand our objective before going on with the analysis. The purpose of having current division rule is to find the current flowing through each of these resistors. So suppose randomly if you are given a network and you want to find the current flowing through resistor R3 and there are 10 resistors connected to it, you can directly apply current division rule to get the analysis done quickly as far as possible. So V is equal to IR according to Ohm's law. So what what can be written? So we can write V is equal to I1 R1, that is the overall drop across this. So I clearly mentioned in my previous video that the voltage drop across this 2 points will be the same. Whatever is being supplied will directly appear at these two terminals. So V can be written as I1 R1. So again, V can be written as I2 R2 as well. So the currents might be different, but the voltage appearing at this point is same, isn't it? So can we write this as I1 R1 equal to I2 R2, because the LHS expression, the term is the same. So we are equating these two expressions, and you will be finding the value of I2 from here. So I2 can be written as I1 R1 by R2. So we'll be transferring R2 in the denominator. You'll be getting this equation. So let us have this as one of the equations. Remember this. So the overall current flowing through this network, I clearly mentioned with respect to KCL. So the sum of currents entering the node will be equal to the sum of currents leaving. In this case, the sum of currents entering is I at this node, and leaving currents with respect to this node. Observe carefully. With respect to this node, I1 and I2 are leaving currents, and with respect to this node, I is the entering current. So usually what kind of mistakes we tend to make is I is entering, it is in downward direction. I1 is also in downward direction. I2 is also in downward direction. So all of them should be summed up together and equated to zero. That's very wrong. That's not the analysis that is supposed to be. We have to consider a particular node when we are applying KCL, and we will be using the law that is clearly mentioned with respect to the statement. So I is equal to I1 plus I2 in this case, because I is entering, I1 and I2 are leaving. So in this case, can we write the expression of I2 here? Whatever we have got, I have substituted here I1 R1 by R2 from this equation. So next step is I will be taking I1 common throughout and write this expression as 1 plus R1 by R2. So I'll be able to do it, right? So once this is done, what is the next step? I'll be taking LCM. R2 will be taken in the upward position. So I is equal to I1 into R1 plus R2 by R2. So once we have this, so we can write I1 is equal to I into R2 by R1 plus R2. So in this expression, I will be transferring this term to the LHS. So you'll be getting the value of I1. So I1 is equal to I into R2 by R1 plus R2. So we have I2 is equal to I into R1 by R1 plus R2. Again, with respect to I2, we can similarly write it as I into R1 by R1 plus R2, because here you can clearly make an observation. Current flowing through the branch I1, resistor R1, is equal to I into R2, the opposite resistor that is there, divided by the effective resistance that is there. So similarly, I2, if you are finding the current flowing through this, can we write it as I into the resistance of the opposite branch R1 divided by R1 plus R2, the effective resistances. So what can be concluded with respect to current division rule? One common analogy with respect to this is that Ix can be written as I into resistance of opposite branch divided by sum of resistances. So if you are finding I1, so I is common, you'll be finding the current first, I into resistance of opposite branch. So if you're finding with respect to R1, the resistance of opposite branch is R2. So you'll be writing R2 divided by R1 plus R2. Similarly, if you're doing for the resistor 2, I2, so you'll be substituting X is equal to 2. So I2 is equal to I into resistance of opposite branch, that is with respect to R2, opposite branch is R1. You'll be writing that value, and you'll be entering the sum of resistances in the denominator and find the value. So by this rule, we can find out the value of the current flowing through the individual resistors that are there. So this is really helpful in that case, isn't it? So these four important concepts that is discussed in this video will be extremely helpful for solving any number of problems with respect to networks. So that's it for our discussion for today. If you like this video, please do like it and subscribe to our channel for regular updates. If you have any questions, please do let me know in the comment section below. Thank you.